Hello friends, welcome to my channel Physics for You. In the last video we have discussed about the Einstein's theory of heat capacity. So this article was not completed in the last video because it is a little bit lengthier article. That's why we will make 2 or more possibly 3 videos on this article. So yes, I will recall whatever we have seen in the last video within 1 minute, and then we'll go to the continuation of the last video, right? So in the Einstein's theory, we know that we have already seen one theory, which is classical theory, and classical theory is having some drawback. That the major drawback is it does not work very efficiently at the low temperature, and that's why Einstein came up with a new theory which will work at low temperature as well as high temperature, right? And for that purpose, Einstein has had some assumptions initially. So some assumptions are as it is, which was already we have seen in case of our classical theory, but some assumptions are new. So the first assumption he has considered it is that atoms are identical and independent harmonic oscillator. Yes, it was as it is. Again, second one, we have seen the n number of three-dimensional oscillators can be considered as 3n number of one-dimensional harmonic oscillator, because solving a one-dimensional problem is easier as compared to the three-dimensional problem solution, right? And again, we have considered the same vibrational frequency to all the oscillators, that is omega here. Then this one is a major and what we can say the more different assumption than of our classical theory, which is what this one, fourth number, that is discrete energy spectrum. Because here assumptions, or in this assumption, what we as Einstein consider is that when we are talking about the harmonic oscillator, so those harmonic oscillators now in Einstein theory are not classical harmonic oscillator, rather they are quantum mechanical harmonic oscillator, and which have a discrete energy spectrum than the continuous energy spectrum. So in classical theory we have seen the continuous energy spectrum, but in quantum theory but in Einstein's theory the energy spectrum will be discrete. So discrete energy spectrum means each and every energy value is different. And the last assumption, or the second last, any oscillators may present in same state, we can call it as degeneracy. And yes, the distinguishable particles, all atoms are considered as distinguishable particles, and they will obey the Maxwell-Boltzmann distribution, energy distribution. So with these assumptions we have reached up to so initially we have considered Einstein's take the help of Planck's quantum theory, and by that he has considered this energy equation E is equal to NH cross omega. And then yes, by if we consider wave mechanics, or by the wave theory, again we got this equation n plus half h cross omega. And even if this n value is 0, we have some energy, or that means that particular solid will have some energy, that E0 is equal to h cross omega by 2. That energy is known as 0 point energy. That means even at 0 degree Kelvin, whatever may be the energy, which energy this one is the vibrational energy. So at even absolute zero temperature, so this 0 Kelvin means absolute zero temperature, that is minus 273 degrees Celsius. So even at such a lowest temperature, atom does have some vibrations, because yes, it have some energy means yes, that energy is coming from the vibrations. That's why that energy is also known as 0 point energy. Okay, now then after we have considered the MB distribution energy formula for the average energy. In that we have substituted our En is equal to n plus half h cross omega. Yes, En plus half h cross omega. Then yes, it is not integration, because whenever we are dealing with a discrete system, integration has to be replaced by the summation. Okay, in continuous system we have taken the integration, but here in discrete system it has to be replaced by the summation. So then we'll for our simplicity we have considered that h cross omega by kt, moreover negative h cross omega by kt as x, and then we have expanded the series for more 3 or 4 terms. You can expand up to 3 or 4 terms, doesn't matter. Minimum 3 terms you have to expand, so that you will understand the continuity, or you will understand some common thing regarding the terms. So what we understand is that this denominator, actually this numerator is a derivative of denominator, and that's why we have written this as d by dx of log of this denominator, because we know that the derivative of log is 1 by x. Derivative of log x is 1 by x. So for this equation we can write a little bit simplest form in terms of derivative, that is d by dx of log of this series. Again in that particular bracket we can take a common, that is e power x by 2. If we take the common e power x by 2, we got in the bracket 1 plus e raised to x plus e raised to 2x plus e raised to 3x and so on. So up to this we have seen in the last video in very detailed manner. Now here this equation we have to use one standard series, and that one is this. So what we have here I have written, but this series log of 1 plus e raised to x plus e power 2x plus e power 3x and so on. So that series will be negative of log of 1 minus e power x, or we can write in reverse manner, log of 1 minus e power x is equal to negative of this. So what we get, instead of this bracket we can substitute simply this one, minus log 1 minus e power x. Okay, right. So again we know that the log basic rules, if log a by b is there, then we can write log a minus log b. So again we will use here. So what we have here, h cross omega as it is d by dx of, now instead of this log of this particular term we can simply write, or first of all we will expand this, because log of e power x by 2 into this bracket. Okay, so let us split this and we can write here, since log a into b, we can write log a plus log b. So that's what we have written here. Here we have to split this. So e power x by 2 log plus log of this particular term. Okay. Now this instead of this log, this series we can substitute, and that is nothing but minus of log of 1 minus e power x. So that's what I have written here, minus of log 1 minus e power x. And now again this log and this exponential will get cancelled. So simply here x by 2 minus log of 1 minus e power x as it is, d by dx as it is, and h cross omega which was already taken common, so it was as it is. Right. Now let us take the derivative. So h cross omega as it is outside, derivative of x by 2, 1 by 2 as it is, derivative of x with respect to x will be 1. That's why minus 1 by 2 minus, again derivative of log, we know d by dx of log x will be 1 by x. So derivative of this bracket is minus as it is, log of derivative is 1 by 1 minus e power x into again derivative of this bracket by our chain rule. So derivative of 1 is 0, it is constant. So negative of e power x derivative will be e power x. So it is in multiplication at the numerator. So it is as it is. So this negative becomes positive. So half as it is plus e power x, and in the denominator 1 minus e power x. Okay, right. Now let us substitute the value of x. Or first of all let us multiply by this h cross omega. So multiplying h cross omega to the bracket, so we got h cross omega by 2 from the first term, and in the second term h cross omega will be in the numerator, and let us divide this e power x on the numerator and denominator. If I divide e power x here and again e power x here, so what happens? See here, e power x in the numerator will get cancelled. In the denominator we have 1 minus e power x, and we are dividing it by again e power x. Okay, so let us divide separately, e power x minus, now this e power x get cancelled, it is 1, and this e power x I can write e power minus x minus 1, and that's what we have written here. Okay, so why it is e power minus x minus 1? So we have divided numerator as well as denominator by e power x. So numerator e power x get cancelled, and in the denominator it becomes e power x minus 1. Now finally substitute the value of x, whatever x, that is not the actual term which is present in the derivation, but we have took it as for our substitution for simplicity. So what is x? Minus h cross omega by kt. So first term we do not have any x factor, in the second term only one x which is in the denominator, h cross omega as it is, and e power minus x, e power minus, already here it is minus, and again x is again minus h cross omega by kt. So minus gets plus, so it is e power h cross omega by kt only. Okay. Right, then what we got, equation number 5, that is average energy, which is E bar is equal to h cross omega by 2 plus h cross omega divided by e power h cross omega by kt minus 1. So that is average energy of one oscillator, right? So in equation 1 it is used instead of equation 3, then value of the average energy will be this one, because that means what, if we have used the another equation, that means which is given by the Planck's theory, then we would have reached up to this equation. That means instead of this equation we will get this equation, that is equation number 6. And what is the difference between these equation 5 and 6? Only this term, that is h cross omega by 2. That is the difference of 0 point energy, right? So if we get that, then the 0 point energy, which is the temperature independent term, that means this 0 point energy, whether the temperature is maximum or minimum, that will be there always. Okay, so even at the 0 degree Kelvin also we have some energy, and that is h cross omega by 2. So either you can use the equation 1 or equation 3. Again you will get the same value, only the difference will be this one. Okay, now so by the quantum mechanics we got equation number 5, and when we can say even at the 0 temperature also we have some energy, that means by the quantum mechanics, or according to the quantum theory, atoms will have some vibrations even at very lowest temperature, that is at absolute 0 temperature. So this energy actually does not contribute to the specific heat, so because it does not have any temperature dependence, but still we have some energy. So this is not the energy which is finally going to contribute in our specific heat of that particular solid. Okay, but yes, we have to keep in mind that energy. Now let us consider the internal energy, because what we got in equation number 5 is what the average energy. So this is what average energy, and moreover it is for only the one harmonic oscillator, moreover quantum mechanical harmonic oscillator. Now let us find the internal energy. So obviously, so how many number of such atoms we have? 3n number of atoms. Or how many number of such harmonic oscillators we have? 3n number of harmonic oscillator, and therefore the total energy will be 3n into that E bar, because this E bar is for one harmonic oscillator, and how many such we have? 3n number of harmonic oscillators. So 3n into the energy of one harmonic oscillator, so therefore it is 3n, and one average energy for one harmonic oscillator will be this bracket h cross omega by 2 plus h cross omega in divided e power h cross omega by kt minus 1. Okay, right. Now just multiply separately and let us write how it will be. It is 3n h cross omega by kt, or 3 by 2 n h cross omega, plus again 3n h cross omega divided by e power h cross omega by kt minus 1, equation number 7. So this is what the total energy. Now let us find the specific heat. Once we got the internal energy, how to find the specific heat? We know that. Let us differentiate that energy with respect to temperature. This capital T is not time, with respect to temperature. We know that the specific heat at a constant volume. Again, moreover, whenever we are dealing with the solid, so it is always with constant volume. So it is dou E by dou T. E now here it is internal energy. So dou by dou T, that is derivative. And what is internal energy? This is in equation number 7. So again directly we have taken the separate derivative, 3 by 2 n h cross omega plus d by dt dou by dou T of this second term, that is 3 n h cross omega divided by e power h cross omega by kt minus 1. Okay. Now again here we know that this 0 point energy do not have any temperature dependence, that's why its derivative will be 0 directly. And in the second term, yes, we have derivative the temperature dependence term. So therefore we will take the derivative. So 3n h cross omega, it is constant taken as it is. Again now we have the derivative of this one, d by dx of, if we have such a derivative, d by dx of x, so its derivative will be minus 1 by x square. So here we have the derivative of 1 divided by e power h cross omega by kt minus 1, that's why its derivative will be minus 1 by whole bracket square. Let us consider now this is x, right? So derivative of 1 by x is minus 1 by x square, that's why it is minus 1 divided by this bracket square. But this is not the end. By the chain rule we have to take the derivative of this bracket also. So by the chain rule, derivative of this bracket, derivative of E1 is 0. That's why derivative of e power h cross omega by kt, it is as it is, e power h cross omega by kt. Again, this is not the end. By the chain rule, we have to take the derivative of this exponential term. So in the exponential term, h cross omega by k is constant. So here we have written h cross omega by k, and derivative of 1 by t. Here it is simply derivative of 1 by t. So its derivative will be minus 1 by t square. So again here it is minus 1 by t square. By this formula, derivative of 1 by x in general will always be minus 1 by x square. So it is derivative of 1 by t, it is minus 1 by t square. Okay, so very simple. Let us see what happens in the next step. Right. So first term got 0. So 3n, I have written here 3n k. So So why 3nk? Because already here it is h cross omega, and here also we have in the numerator h cross omega. Okay, again here it is t square. Now this minus and this minus becomes plus, so no problem. So this Cv will be plus. Okay, so h cross omega already it was here, and this h cross omega whole square. In the denominator again we have t square, but we will just multiply and divide this equation by k. So multiplying by k in the denominator, so k into k square. So I can write h cross omega by kt whole square, because already h cross omega here. So h cross omega by kt whole square, and this numerator k is written here. So that's why it is 3nk for simple writing only, into now e power h cross omega by kt as it is, divided by e power h cross omega by kt minus 1, equation number 8. This is what the specific heat when we are talking about the Einstein's theory of solid, in which we can find the lattice heat capacity or specific heat. So this is general equation for Einstein's specific heat. Now for simplicity again we will consider this h cross omega by k as theta e, h cross omega by k as theta e, and that is known as Einstein's characteristic temperature. So let us replace here in equation 8 what is that h cross omega by k, e by theta e. So we can rewrite the equation, that will be now Cv, that is specific heat at constant volume, will be 3nk as it is. H cross omega by k is theta e, so theta e by denominator temperature as it is, its square, e power again h cross omega by k is theta e by t, and in the denominator e power theta e by t minus 1. Now this equation number 10, this equation number 10 is the more specific equation for the lattice heat capacity or specific heat Cv according to Einstein's theory. So what is that? 3nk theta e by t whole square into e power theta e by t divided by e power theta e by t minus 1. So here what is that theta e? Theta e is nothing but h cross omega by k, and that is called as Einstein's characteristic temperature. Okay, so yes, obviously this is what the general equation we got from the Einstein theory, but we know that why we went for the Einstein theory, because there was little bit drawback in the classical theory. That means classical theory does not work very well at the low temperature. So we have to check whether this Einstein's theory work at the low temperature as well as at the high temperature. So simply what we have to see, the low temperature behavior and high temperature behavior. But yes, today we will stop here, and that we will see in the next video. That will be the last video when dealing with the Einstein's theory of heat capacity. In that video we will see both the cases at low temperature as well as at high temperature. We know that already high temperature, for high temperature we have the classical theory, but problem is what is with low temperature. So we will see in the next video whether this Einstein's theory works very well at the low temperature or not. Okay, so till then you please study this article in the last video and from this today's video. Take your notes, and if you have any problem with any step, any doubt, you can post in the comment box. Otherwise, if you feel this is value addition to your knowledge, then like this video, subscribe to our channel for more such videos, and go to the playlist and watch the concerned videos. And yes, we'll meet in the next video very soon with this continuation of this article. Till then, take care and keep learning. Thank you.